Hey, this is Horner. We're going to talk a little bit about 2D motion. This chapter, remember, is in your book, and your book is online. These notes will go through and really describe things a little bit better than probably what you could read, although you can read that and do this, and you should be good to go. For two-dimensional motion, we really focus on acceleration. We focus on acceleration because things tend to go in some sort of curve. So the average acceleration for a particle as it travels through some sort of acceleration, I guess that's redundant, but nonetheless, is equal to the change in velocity over the change in time. You'll notice these little arrows indicate that both of these items are vectors, and the lack of an arrow here on time indicates that it's a scalar. There are two ways that we know that a object is accelerating. The first one is we can see that it has a change in speed. Notice there's no arrow above it, so this is really just a change in speed. So they indicate that here, or the direction of the speed can change. And if you know that the object has changed direction, that we also can say that it is accelerating. You can have either of these, or you can have both. And so we'll show you that here in an example or two. For the next slide, we're going to talk a little bit more about how to find the acceleration vector. So let's say that I am traveling in one direction, we'll call it with a speed of Vn, and then I change my speed to make it Vn plus 1. In order to add the two, I go ahead and draw the velocity vector n plus 1. So that's the second one you'll notice. I'm going to take the first one. I'm going to just draw anti-parallel. I'm just going to go same plane, but I'm going to go the opposite way. And I'm going to take this one and I'm going to attach it so that it is a head to tail configuration. So now what I've done is right here. At that point, I'm going to then draw a line that connects the butt end of the first arrow to the head of the second. So we could call that butt head. And that line right there then is our change in velocity. And if you remember, change in velocity over change in time then would be our acceleration vector. And that tells us what direction it's going in. It doesn't really tell us how long it should be because we'd have to know the change in time. But it does tell us the direction that that vector should be going in. For the next slide, we have Maria's Ferris wheel, and we want to know the acceleration vectors for each dot. So to do these, we can actually just use this diagram, and you'll notice we're going to take our Vn plus 1, we're going to take our Vn, and we're going to make it go in the opposite direction with the same magnitude. Now we're going to move that one, so I'm going to grab a hold of it here. Oops, maybe. I'm going to grab a hold of it. I'm going to move it so that it is going from head to tail. And then I can draw my acceleration vector. Oops, need to go back a slide here. I can draw my acceleration vector connecting the butt of the first arrow to the head of the second, and that is representative of the direction of the acceleration and not necessarily its length or its magnitude. If you do that for each one, you'll notice that all of the acceleration vectors do point to the center of a circle. So when we've talked about centripetal motion, we always have told you to trust us that it does point to the center. Now this really proves why your change in velocity should be able to show us the direction of that acceleration. We don't know the magnitude again, we just really know the directions from each and every single one of these. For the next slide, we're going to think about a ball as it goes down a valley, speeds up, and then slows back down, and then comes to a stop, and then comes back the other way, and it would just keep going back and forth forever as long as there's no friction. They want us to draw a complete motion diagram of the ball showing the velocity and acceleration vectors. So we'll do that here. This is the solution. We have a velocity starting off at the top, and you'll notice that as the ball moves down to the bottom, it speeds up, and then as it moves back up the other side, it actually slows back down. As long as the only thing that's happening is the velocity is increasing, we can draw our acceleration vectors parallel. So here, as the velocity increases, and as long as there's no direction change and only the speed is changing, these stay parallel. The instant that we start to get a little bit of a curve here, both the speed and the direction are changing. We need to start drawing these arrows that indicate the direction of the acceleration. Don't worry too much about the length of these arrows. We're really worried about the direction of the arrows. So let's add a couple. We're actually going to add this arrow and this arrow together. So we always leave the second arrow where it is. We're going to take the first arrow. We're going to draw anti-parallel, so we're going to go in the other direction. Then we're going to take this one and we're going to move it so that it is head to tail. and then we're going to draw a butthead line. So this butthead line would be this acceleration vector. Notice that this just shows us the direction again and not really the magnitude. We could do the same thing for the next one, where we take this one, we draw anti-parallel, then we grab a hold of this one, and we move it over here. We can get rid of that guy because he just kind of tagged along. And now we can see that the direction for this next one is in this direction. We've done that all the way across. On these, notice that just because our velocity is changing and our speed is changing and not our direction, these are both parallel again. However, we do call this anti-parallel, and it's anti-parallel because it is slowing. On the other side, it was parallel because the speed is speeding up. And that is how you would look at a motion diagram for a ball going down. Oh, if you had a bowl and you let that ball go down and it kind of goes back and forth. For the next diagram, we're looking at the acceleration vector. We can actually analyze the acceleration vector. If the acceleration vector is perfectly parallel, okay, so it's in a 0-degree orientation with velocity, then we say that this piece of acceleration causes the object to change speed. If I have another piece and it's perpendicular, that perpendicular piece of the acceleration is the thing that causes it to change direction. So now we can look at this acceleration vector and we say we're both speeding up because there is a parallel component and we are changing direction. So as we kind of moved on, this ball would continue to curve in this direction, which is just an indication of what this acceleration vector does. For the next slide, we're going to further flesh this out a little bit. We have two positions. We have a position graph for y and for x, and here we've just shot a cannon, and that cannonball comes out, and this is our trajectory. If I go from just a point here on the axis and move up to here, we could say that is the change in position for that cannonball. And that change in position is just the x component and the y component, and you'll see that we're adding those two together. So here's the x component, here's the y component, and if we add those, we end up with this line right here, which is our r. And it's got a line on it because it is a displacement and not a distance. The distance would actually, you'd have to measure the curve here. So we're really just looking at change in position, or the resulting position is just the sum of the x and the y components. On the next slide, we're going to further this a little bit more by looking at two of those. So here we've got a first change in position. Here we've got another change in position, or two displacements. The change in those displacements would give me the average velocity. So we could say the average velocity is the change in displacement between R2 and R1. Or we could say it is the change in the y and the change in the x components, and so you'll see that notation here. For this to be even better, what we can do is we can start by saying, here we've got a change in position. Let's move it back a little bit and keep moving it so that we approach a time of 0. So here we've got a time, we've got a little less time, and as we get closer and closer to 0, so our limit is delta t is approaching 0, we can see that we end up with dr over dt, and that is basically just the change in the x plus the change in the y over dt, and we end up with a velocity. A velocity in the x is dx over dt, and a velocity in the y would be dy over dt. So as point 2 moves closer to point 1 again, we see that we're getting closer to 0, and now we end up with a tangent line. Remember, tangent lines to this curve is going to be our direction of our velocity. So let's look at this next slide. The velocity in the x is v cosine of the angle, so that's this one. The velocity in the y is going to be v sine of the angle, so I'm actually going to draw another line here. I'm just going to draw it straight up. This is going to be vy, and that's equal to v sine of the angle. They put it here. I like to have it on this side so you can see how it relates to the angle. If I have these two components and I want to know what this line is, I can just use the Pythagorean theorem, so you see that two ways. And if I want to know the angle, I can just say the angle is equal to the inverse tangent of the speed in the y divided by the speed in the x. And so that makes it a little bit easier to see too. Going on to the next slide, they want you to be careful that the tangent to the trajectory does not tell us anything about how fast the particle is moving, okay? This is just the direction, so this is merely the direction. If I want to really know the value, I need to find the slope of a curve. So I would draw the tangent line and have to find the slope. This tangent line is just showing the direction because it's y versus x. This slope is telling us the value of the velocity because it is position. We usually use x for position in meters, and then time here is in seconds. So the value of this slope is going to be our velocity, and the value of this slope is really not a value. It's just a determination of the direction of the velocity of the particle. So that's how you get both. The next slide tells us about a example problem. We want to describe the motion with graph. So you have a particle's motion. It is described by two equations. Our x position is just 2 times t squared, and our y position is 5t plus 5, and those are both measured in meters. Our time is measured in seconds. They first want us to draw a graph of the particle's trajectory, and then they want us to do some calculus in order to find a graph that would show the particle speed as a function of time. So the first thing we need to do is fill in the x and the y's. We're not going to fill in the v yet, but if we fill in the x and the y, we can find the points and draw a smooth curve. So for this first one, if we plug in 0 for time, obviously this is going to be 0. I'm going to change colors here. Let's make it red. So this is going to be 0. At 1 second, that would be 2 times 1 squared would be 2. At 2 seconds, 2 squared is 4. 4 times 2 is 8. 3 seconds, 3 is 9. 9 times 2 is 18. And then finally, 4 squared is 16. 16 times 2 would be 32. So those are our x positions. Our y positions are a different equation since they're independent of each other. So the bridge here between the two is time. So 5 times 0 is 0 plus 5. So that would be 5. Next one would be 10 because 5 times 1 is 5 plus 5 is 10. 5 times 2 is 10 plus 5 is 15. Then 20 and 25. At this point, I would need to draw a graph. If I draw a graph and I have y and I have x, and these are both measured in meters, and I plot that, I should end up with a square root function. So I would do that on Logger Pro. If you do that on Logger Pro, you should see that curve. You also could do it on your notes. Just do a really nice, easy sketch. Put your points in. Just watch out. Your x has got to go from 0 to 32, and this one's got to go from 0 all the way up to 25, and you want to plot those starting at that 5 point. At this point, we're going to leave everything that we have here except for this graph. So let's go ahead and just erase the graph that we have here. And on the next slide, it talks about going through and trying to figure out the value for velocity. So we want to find Vx and we want to find Vy. We're going to use our equations that we have here. And we notice that we're doing the derivative for each one of the equations that you see. So for Vx, we know that that is 2t squared, okay? Oh, and this is really, sorry, this is x, is 2t squared. If we want dx over dt, which would give us velocity, we need to do the first derivative. So we would do 2 squared would be 4, and then this just would be t. So that is our first one, and that's measured in meters per second. For dy dt, we'll have our equation here. I know that I would take, this is t to the 1, so 5 times 1 is 5, and that's just equal to 5 meters per second. This 5 doesn't have a value for t. T here is 0. 0 times 5 is 0. And then this t goes away because it reduces down. 1 minus 0 would be 0. So we have dy dt is 5 meters per second. So now we have the values for Vx and for Vy. So this is really Vx. This is really Vy. We can now create an equation for it. Remember we said that the final velocity should be equal to the square root of Vx. So that would be 4t. So that would be 4t squared plus, and then we have 5 squared. So this is equal to the square root of 16t squared plus 25. Now what we can do is go back to our previous slide. So we're going to go back and we're going to plug in our velocities. So I'm going to get rid of how we got there. And we're going to plug all our velocities in. So right here, this velocity, if we have 0 time, this would be 0, and the square root of 25 would just be 5. For the next one, we plug in for our time, it's 1. So 1 squared is 1, 16 plus 25 would give you 16 plus 25, ends up being 41. You do the square root of 41, and you should get 6.4. Similarly, you're going to do 2 here. 2 squared is 4. 4 times 16 plus 25, and you do the square root. You end up with 9.4. For the next one, we have 13. And then finally, we have 16.8. If we plot the points for this one and draw a smooth curve, so we're going to go back to the next thing, they want us to draw a velocity versus time graph. So here's our velocity. Our times were 0, 1, 2, 3, and 4. And when you draw that graph, you should get a graph that is a parabolic function. So it should look something like that. I would encourage you to do it on the little piece of graph paper that I gave you on your notes. And then this time is in seconds. And that is the end of the notes.